Usually my chapter is pretty long. Is something like 28 page or 25 page long, and of course it's not like book form, but it's rather condensed form in PowerPoint, but with my explanation, it's gonna take some time. And a quick review, because Friday was off also. Really nice haircut, Jongwon. It's good. So you have my phone numbers and all that. And the measurement quantity as mechanical engineer or ocean systems engineering, and physical phenomena we covered, deterministic and random. So random, I use sometimes random, sometimes stochastic. It's all about the same. So in the art of mechanical engineering, the stochastic process, sometimes you may call as random vibrations. The art is very close. And what we are using, emphasis is different. Emphasis is somewhat different about the halfway. Halfway after is different. But beforehand, mathematical treatment is about the same. Okay, so the book I have been using was two books. One is like random vibration cross correlation by the Bandit. I told you Higyu has it. I checked the Higyu whether anybody really checked out the book to review. Nobody checked out the book. It's last 2 weeks, few days were no class. That's why. But from now on, I have 2 sets of books, so you may check out anytime. If you don't need, don't check out. So Bandit's book was very popular. It came out 2 different forms. I listed 4 books, but 1 additional books, I don't think I put that in, is Random Data. The book name is Random Data. It's Bandit and Piezo, same author. So one passed away, as I mentioned. Bandit is still there. I really hope he's still there. And as I mentioned here, random data analysis and the spectral analysis. One is the frequency domain, the other one is time domain phenomena. So then I go through the deterministic process. Deterministic process, if it's not random, then it belongs to this process. So periodic, non-periodic. Then next I explained about the random process. So then came back to deterministic process, talk about the periodic, and I talk about the non-periodic and almost periodic. What's almost periodic? Anybody can address on that? Well, it's too early, maybe. So, almost periodic. So think about it. I explained. And transient, briefly explained, and now is I'm going to push a little bit hard on that. And this periodic functions, if it contains many different frequency components, to really investigate the details of the frequency content, then you have to use the Fourier series. That's what I explained so far. And I'm going to talk more about the Fourier series. It's like a classical forms, and you have a polar forms, and you have exponential forms. It has, it's all same. All three forms, just wearing different clothes, it's all same. But there is a convenience of using different forms. So you should be able to really learn that. When you go back, Higyu sends you the homework number 1, which is very reasonable. You should finish that homework in about 30 minutes or less. If you have to plot the curve, maybe an hour, okay? It's not difficult, but do it with understanding. And I'm gonna do the different forms of the Fourier series today, and also Fourier transform will just follow the right after. It's worth to review, because if you look at my way of doing it, I always review, then jump into it, rather than just jump by just assuming you know everything. Sometimes you learned 2 or 3 years ago, then you can remember. But if I spend like 10 minutes, then that's worth it. Then you just get it back right away, and you can pick up very quickly. Deterministic, random, stochastic, stationary process. Another case is the non-stationary process. When I talk, I want you to think about it, just to visualize what you learned, then just remember. Okay, that's what I want you to do. Stationary, the most important process is algorithmic process. Youngyu and Yunsuk, what's the algorithmic process? Say, I don't know. You don't know because you didn't study. Until last night you didn't study yet, but you will. Nothing to worry, you will. Okay? You will. You all are not dumb, you are all smart. You will do that. Algorithmic process. What's a stationary process, Gustav? What's a stationary process? What's the difference between the algorithmic process and stationary process? When you learn, I want you to learn correctly, okay? As correctly as possible. Last Wednesday we did, and Friday we were off. And if it's not stationary, it's non-stationary. So as the name implies, when you hear about the stationary, then something not common. Stationary means it's something common, something are same. So stationary, even if time history is concerned, nothing is really same, but statistically wise, when you hear about stochastic, then you have to deal with the statistics. So statistics, probability is a core of the random process. It's a core. Without the statistics, you can't explain anything. You cannot. Nothing works. So that you have to remember. When you hear about the stationary, algoric, then there is some common stuff. Common stuff. It's called the stationary, something common, statistically common. Not word by word, not the deterministic sense, okay? So, deterministic data, sinusoidal periodic data, is a complex periodic data, and I give you a little bit appetizer. This is appetizer, and today I'm going to give you the full set. Today is going to be a full set. This is kind of a classical expression of the Fourier series. This is like exponential. This is a polar form of, just think it's a name. Okay. It's a polar form. This is funny. It's not working sometimes. Polar form of Fourier series. Then what does it do? Not only amplitude distribution, amplitude, the summation of frequency, Fi or F1, that's a fundamental frequency or first frequency. Then the Fn, n times F1. Sometimes I expressed that as Fn. Fn is equal to the n times F1, right? So you can tell the amplitude, not only the amplitude distribution, but also frequency contribution to the particular frequency. So this is something like, this is like 1 times first, or the fundamental frequency has a large contribution to the total amplitude. So this case is very small, vice versa. So that's the polar form of Fourier series. Fourier series is a combination of amplitude and frequency contribution. Remember 2 things. That will go move to spectrum. Okay? Almost periodic. Looks like a periodic, but it's all periodic means it has a particular period. Okay? Then almost implies this Fn over Fm is not the rational number. To qualify to be a rational number, Fn has to be integer and Fm has to be integer, and if you express this frequency as the fraction of integer, then you can say that that's not almost periodic. But this case is all integer. You can multiply 2 pi, but that cancels out already. So if you have a square root of 50, this is example, then that's not the integer. So then you have to be careful. So in the homework today, which I assigned today, is like to get some feel and some experience. Then you can really plot the graph, and you can judge yourself with a confidence that that's really almost periodic. Oh, that's a stationary. Oh, that's allogotic. So such a decision you have to make it. Okay, it's practice. Practice. This is a transient, a non-periodic data. Transient, non-periodic data. Typical, square wave. This guy is a damped, damped signatures, because you don't have, here is outside the door, you have a damper, shock absorber. It slowly releases the motion, then it's slowly coming down, which is e to the minus st. Okay, this is really shock absorber. It just comes right straight down. And this is really, if you throw this into the frequency domain, of course we're gonna all do this later time, or you may have done this before. Then in the frequency domain, how that curve look like. In the frequency domain, looks like this is related to this. So at the particular frequency right here, then it has a contribution. So this is something like a resonance situations here. This is a static, F is equal to 0. Okay? So this is what the situation. So here is a cosine BT. BT, B is 2 pi f. So if you divide B by 2 pi, then you have the dominant frequency. And for the square wave, you have multiple. Think this way, always common sense first, before you try to evaluate the math. So to generate such a rectangular pulse, you have to have many combination of sine and cosine function. Could be small frequency, at the beginning is a large frequency. So just use your common sense, then find out the reasoning, rather than try to digging the math itself. That's much easier. Then once you really learn using the physics of it, then it will stick in your brain, will never lose. Okay? Then a continuous spectral representation for the transient data may be obtained using Fourier transform. It's gonna be today or Wednesday. Okay? So yeah. Now slowly getting into the, it's not only for Yun-Suk, but this is for everybody, because today is really the beginning of the first class. What's his name? I forgot his name. 한성. 아니, 또 한 사람 있었지, 여기. 강헌. Yeah, 강헌. Yeah, he, of course, he dropped out, but anyway. So, now we are dealing with the random data. All this, the wording, I want you to really taste the wording. Taste is different from reading. Taste means really, not just looking, look carefully, and understand the meaning behind the paragraph, and really taste on it. Because when I prepare, I didn't just pick, and I read all the book pretty thoroughly, then and get the really meaningful phrases and where I want to emphasize it. That's what I did here. And sample function, random process, sample record, stochastic process, random process. This is different. Sample function is, what does it mean, sample function? 주성이. Sample function, what does it mean? Sample function is one record, right? One record is sample. Individual record is a sample function. Okay? Single time history representing a random phenomena. Gust of wind. This is noise in the generator, maybe, yeah. Thermal noise generator output. So it's all the noise. It looks like just a noise, but nothing but noise. But when you throw into frequency domain, when you take a Fourier transforms, when you take a Fourier series, then its personality revealed by itself. Sidetrack. I mentioned already to other courses and all that. You will never have a 소개팅 and marry her. You have a 소개팅 sometime? No? I learned the name 소개팅. 한석이, you do 소개팅, right, sometime? No? Bad. You should. 정환이, you do 소개팅? Sometimes, right? Yeah, make sure that before you go 소개팅, have such a nice haircut. So nice. Why you do that? Why throw into frequency domain? If everything can be done in time domain, why bother to investigate the frequency domain? What's happening? What's in the frequency domain? Idea. Why bother to do the 소개팅? Why 소개팅? One of the reasons is whether the parents introduce are really wonderful girls, you may not like her. Even if you do, somebody arranges 소개팅, you may not like her. Because personality, if it's mismatched, then it will never resonate. If it's resonate, then it's a problem. So that's what the 소개팅. So I already used this example in my class. Maybe not. I have a twin daughter. They're all grown up, but when they were born, I sit around in the living room, they turn the music on. Then it was a very classical type of the music. My two daughters, girls, two daughters, they sit there next to me, then they don't do anything. They don't do anything. So I said, oh, it's interesting. They don't do anything, just sit next to me, half asleep. But I changed it to like a rock and roll, fast music, you know, and caras like this, or 소녀시대, you know, all that. They don't sit there. They are not sleepy. They stand up and start twisting the body. Why? Body frequency is resonate to music frequency. So they really resonate so well. That's what you want to see, resonate. If you throw the signature, this noise type the signature, when you throw into frequency domain, then what happens? You will see the frequency content. Whether it's going to be around the 25 hertz, whether this is around the 40 hertz, you would know that. You don't have to guess. So that's the reason. So you have to throw into not only classical music, if you make it really louder, for them, when they were small, it was a noise. You know, they just sit there, do nothing. It didn't move their heart. But when you change it to other rock and roll type, then they all resonate together. So that's the main reason. Remember, here I'm dealing with the time domain signatures and also the frequency domain signatures. You can add into the thermal situations if you that's another important parameters. Okay, you can treat that thermal effect as a random, the variable. Okay, whenever you're dealing with the reliability of the system, how reliable? When you say about the reliable, that related to the randomness, that related to the stochastic process. And you will never say, oh, 100% reliable. There is no such a thing as 100% reliable. Why? Dealing with the statistics. So you have 90% success rate, vice versa. Random process means it's a family of random functions. Okay, so simple. Random record 1. Random process is a family of the sample function. This is what we are talking. Okay. Anybody can explain what's the stationary using this particular the figure? I want you to talk. Anybody can explain about what's the stationary process using this particular the figures? Anybody? No? Yongbin? Yongbin, right? Yongbin? 크게. I think you know what you're saying. You know. You know. 성원 한번 해봐. 성원? No? 성원, you want to try to explain clearly what the stationary process using this figure. This is the best figure to explain. Where did you cut your hair? What's the, I mentioned last week, I mentioned to you kind of a very fundamental, the statistical parameters to use as a measure of saying stationary, algorithms and all that. What's the three particular parameters? 3 or 4 as of right now. What is it? One is mean value. Second, mean square value. Third is called the variance. The variance. So that's three parameters. The variance is a square value. Okay? The variance is mean square value about mean value about mean square value about the mean. And mean square value is about the 0. We talk about that. Mean is mean, average value. And another parameter, statistical parameter I mentioned last week was autocorrelation function. We haven't just pop up and I just explain to you what that is. But it's going to keep coming up, of course. And I am going to explain once more. This is one family of the random, could be a random phenomena. Something like thermal noise, generator noise, or gust wind, it could be, and whatever. This is one record, another record, another record, another record. It could be a whole bunch of records. Something like I mentioned to you, I took a measurement at 10 a.m. in the morning, like today, 10 a.m. in the morning tomorrow, the day after tomorrow, vice versa. Then I'm going to say that this is at time t1. Time t1. It's all in time t1. Here is another time, any arbitrary time, at time t1 plus tau. Tau is the time duration from here to here. Or whole thing you can call as a time t2. Okay? Then you can pick out that amplitude plus, 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 then 1, 2, 3, 4, then add them all, then divide by 4. Then that's going to be simply the mean value. Okay, discrete point, mean value. You can do the same thing, plus, 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 divided by the 4. Then if you compute that mean value, and if you say that, then mean value is very close each other when you measure at time t1 or when you measure at time t2. If it's the same, then you can say, wow, that's a stationary process. Stationary. But not just the one. You have to have at least 3 to qualify. And you will take the mean square value. Mean square value, you have to compare. Then if it's close each other, that's better. And if you compute the variance, if it's the same, then you can really say, then that's really stationary. But to qualify for the algorithmic process, what do? If this, whether this time history is algorithmic process or not, you have to do something. What would be it? You take a mean square or variance for the one signal, right? One signature. Then if that is the same as the statistical parameter that you computed at time t1 or time t2, then that's algorithmic process. And many situations, the signature falls in that category, okay? And as you will see. Today is like a first day of the lecture, I feel, because almost everybody's here. All the drop add is all done. So that's the reason. So I demand you, studying is a fun, So you can really study. Look at first my older notes. It's about 20 pages so far, and to fully understand. This is the notation I'm using. Mu is a mean. Mean or mean value is the same. At time t1, x is a random variable, one number. You pick out the one point at time t1 right on the curve, that particular value. So E is the same as expected value or mean value. Expected value is all same. And limit n goes to infinity, 1 over n, and xi is ith, the time series, you can say that. Mean square value. An autocorrelation function. Autocorrelation function at time delay tau. Tau could be a variable. Tau is time distance between the 2 points, okay? So over here, I change my note. Here, subscript, put the I here. Subscript I here in a correct sense. So right here. If you don't, that's okay too. It's not critical to anything. Okay? For the algorithmic, this is ensemble. Ensemble means the whole family. Ensemble average for non-stationary and stationary. Stationary, non-stationary doesn't matter. When you're dealing with for example, average at time t1, average at time t2, okay, there is no demand saying that this has to be the stationary. If the statistical parameter is equal, then you can issue saying that that's the stationary. If the statistical parameters at time t1 and time t2, if they are not the same, that's a non-stationary value. Okay? Algorithmic data, you are dealing with the one time domain signature at the time. One time domain signature at the time. You can compute the statistical parameter for this time domain signature, for that time domain signature, vice versa. Then if this, of course, they must be same. Statistical parameter must be same. But in addition, that stationary process, that value, statistical parameter has to be same. Okay. I repeat the same thing over and over again. So, okay, now, so we reviewed quite a bit. We reviewed what we have done that. So now back into the stuff on page 15, and n number n, limit n goes to infinity. Number of event or number of trier, that's capital N. T is a time duration or period. If that n or time t, number of triers or time t, never approach to infinity. That's what, if it's always infinity, then you are studying the physics subject, not engineering subject. Engineering are based on always not infinite but finite. There is an arrow involved. I mentioned to you last week a few times already. Can we live with the arrow? Our answer as engineer is yes. We can live, we can tolerate with a few errors in it. So we can do infinite, because infinite, we have to live lifelong without doing anything. That's not infinite. Infinite goes beyond our death. Keep moving, but impossible to do. So we are dealing with always finite. Okay? Finite duration, time duration, finite number of trier. Then, for example, you throw the dice. Dice is 주사기? What? 주사위? Then single dot. What's the chance that single dot appears up all the time? Well, you simply know already. Say, oh, there's the 6 dots we have 1 out of 6. Then chances are 1 out of 6 it could show up. But you keep drawing, right? But that's a discrete model. That's why you could say, oh, it converges into the 1 out of 6. If it's a coin, you just flip, and what's the chance that top will show up? Half. Approach to half, vice versa. So everything is infinite means produce error in the data. Finite, I can live with error. So that's what that is. Then finite sampling considerations you have to always think. And you have to deal with the statistical sampling error, which is inherent in analysis operations on finite amount of the data. Okay, this chapter 1 is lots of little materials and get you a feel of it. That's rather than blank. I want to fill your heart with a little whole bunch of different dust in there to catch the art. This one, if you look at, I don't know whether you can see this or not, there is a wording. This is like a pipe flow pressure time history, and this is example of, I bet, this is non-stationary. Another word. What does it mean? Non-stationary. There is no statistically the common things here. There is no such a thing as a mean. Okay, that means it's not stationary. So some like the wave forms is what you see here. This is, I can tell without looking, this is impact. Bang, right? Have you seen impact hammer in undergraduate? If you use impact hammer, the force transducers, and the other end goes to the plate, for example, then plate, right at the top of the plate, transducer is mounted, input, output, so then you can get the transfer functions. Transfer functions, then you know where the peak, the frequency is, vice versa. So this is what sort of the things here. And here it could be non-stationary, but could be stationary if it's really little bang rather than heavy, vice versa. And this is the non-stationary atmospheric, the gust velocity. Gust velocity, once you turn the TV once in a while, there is really gust wind in Ireland, in every summer in outskirts of Florida, always they have a hurricane out there. Then all the measurement is just wild and non-stationary. So by looking at this, not clear whether this is a stationary, non-stationary, you have to conduct the testing. For statistical parameter testing, then you can tell whether that's what process that particular signature is. Okay, now quiz. Quiz is like this. My first quiz. It has two sets of quiz here. What kind of random process are they? This is one set of the process, okay? One set of the process. It's a different initial phase angle. The time history portion doesn't end at the same time. It's all different. Look like to get that point here, this has to be shifted down here. This has to go down here. This is way down here, vice versa. So phase shifting is here. By looking at this, what kind of random process or stochastic process is this? That's the question. And amplitude is said is all same, from here to here or from here to here. It's all amplitude is all same. Then question is same frequency, of course. Same frequency. So if you look at if I put that in the ensemble form, like this is ensemble, parenthesis, right? So x naught it's just to give one sample. Okay. Then question is, this is just rewrite this guys in the equation forms. So question is this first set, is this stationary? Or is this algebraic? What is it? You tell me. Second is the same thing. The second is initial phase angle is different. It has a different, the phase angle it has a different amplitude, different amplitude. So another situation, xt x sine is sine okay, is a sine function. Sine 2 pi, is it frequency said is the same? Same frequency. And does it say it's a different initial phase angle? Different initial phase angle. This is a random. Random. This is a fixed. Random. This is a fixed. This is a fixed. So what is it? Is it stationary? Is it algebraic? What is it? So what is it? So you tell me. Start from Yongwon. Its chances to win is about 50-50. Not bad. Okay, everybody you pick one. So I'll list up. First this one. First set. Is this a stationary process? Yes or no? Is this algebraic process? Is this algebraic? Okay. Second, is this, if you express that in the equation form, is that the stationary process? Is that the algebraic process? No. Is this a stationary process? Okay, you haven't decided what to do, then I want you to think, then see me on Wednesday. Give me the right answer. See, this look like that look like that, but sit down, think a little bit. Then you can tell, that's it, that's the way to do. Okay? So I think students are waiting outside, and I'll do.